Yeah, he is also a founding member of quite several academies. Yeah. So then I introduced him a little bit more because maybe you people do not know. Yeah. So I think his first big important work did in China is the develop, lead the design and construction of the battery 3 detector. Yeah. This detector now is play leading role in tau physics and charm physics. Yeah. So particularly for the charmonium-like exotic particle. Yeah. That is his detector and one of their beautiful work. Yeah. And his second important work is the diabase experiment. Yeah, that is his pet project. Yeah, diabase experiment measured one neutrino mixing angle precisely. Yeah, so sorry. This is not only a number. This number is very important. Yeah, it open a big door for the future research. Yeah, and because of this work, he and his team earned the fundamental physics breakthrough award. Yeah. And now he's leading another very important experiment, the Juno experiment, to measure the mass hierarchy. Yeah. Here, any laser? Oh yeah, look, that's the Professor Wang standing in front of the Juno detector. Yeah. So now he's playing with the PMT. Yeah. PMT. Yeah. And indeed, it beside these three important experiments, when he served as IHIP director, he and lead the IHIP constructed a number of big experimental facilities. Yeah. Like here, they have the laser and neutron source and high-energy photon source, all under his leadership, and also some telescope. Yeah. And the most important thing is that Yifang had been supporting our research and education in Thailand in high-energy physics over 10 years, or maybe, yeah, over 10 years already. Yeah. So some example I show you. Yeah. So that's in 2014, and SUT and IHIP signed agreement to support our research and education. Yeah, yeah. So this one is in 2017. Yifang, now then he was the director already. He came to Thailand to give a lecture for Juno School. Yeah. So over there is him. Yeah. Giving a lecture. Yeah. Last year, yeah, he came to Thailand to give a lecture in the Shenyang Physics Congress. Shenyang Physics, yeah. In 2015, SUT awarded Professor Wang honorary doctor degree. Yeah, doctor degree. Yeah. So that I cannot remember which years. Yeah. SUT, I mean Suvarnabhumi University of Technology, and Chulalongkorn University and the NALIT signed MOU with IHIP to join Juno. Yeah, Juno. That's a big help to us. Yeah. So now the Professor Wang is not only busy with Juno, also busy with this one, the so-called CEPC. Yeah. It's a big circle. Yeah. He proposed the idea and now also leading the design of this big facility. We hope this one will fly up. So that will help us to do research in high energy physics a lot. Yeah. Okay. Now it's Professor Wang's turn, please. Yeah. Yeah.
So good afternoon. Thanks to Professor Yan. It's a great pleasure to visit again SUT and also talk to young people. So today I'm going to give you an introduction of particle physics and also a little bit of its relationship with cosmology. In particular, our experimental activities in China and my personal kind of experience. So the topic is called the quest for infinity. So start from small, it's particle physics. So sometimes we also call particle physics or as hydrogen physics. It is actually a continuation of our quest to the infinite small from molecules, atoms, to nucleus, quarks, and also leptons. So indeed, at every stage, let's say at moleculars, there is a new kind of discipline called the chemistry. I'm sure you all know about it. And also for atoms, we have atomic physics, condensed matter physics. And for nuclear, we have nuclei, we have nuclear physics. And finally, we have particle physics. So you see that this is a kind of continuation of searches and understandings of the ultimate small structure of matter. So indeed, in summary, this kind of research is a key driving force for the development of science in the last several hundred years. So if you go to large, that's astronomy and cosmology. You are going to hear the talk by Professor Murayama about the cosmology. It is actually another continuation of the quest that people, even 1,000 years ago, people looking at the sky and try to understand, for example, the sun, the moon, the planet, the star, the Milky Way, and all the way up to clusters and the universe. So this is also a long history of the research. And over several hundred years now, we understood that our universe, indeed, as far as we know, up to the boundary of the universe, is the one coming from a Big Bang. Now, people easily ask you, before the Big Bang, what happens? We don't know. And the people may ask, outside the boundary of the universe, what else you have? And what else you could imagine, we don't know. It's probably up to you guys, young people, to understand this and to solve the problem. But anyway, as scientists, we only tell you what we know, which is a limited time scale and a limited kind of space. So within this space, after the Big Bang, we have a so-called evolution process, which actually follows the physics law. So you can see from this picture, at the starting point of the Big Bang, then there was inflation phase, and then we have so-called evolution of the universe. And all these steps after the inflation, all this process follows non-physics laws, and in particular, particle physics knowledge. So why particle physics is so much related to infinite large? Because when you are infinite small, you have very high energy. And once at the beginning of the universe, at the Big Bang, starting of the Big Bang, the temperature is very high. So temperature high is also energy is high. So the physics at this stage is the same. So you see, it's called the interesting kind of glacial snakes. The large and the small, in the end, they meet together at this point. So this is very interesting that when you study infinite large, infinite small, in the end, they are the same. I mean, it's all follow scientific kind of laws. So what we try to do in so-called infinite small to understand the structure of matter. So the discipline of particle physics actually originates from 50s to 60s, when people start to discover many of the new particles. Before that, it's nuclear physics, and things has been understood quite well up to that time. So with these new discovered particles, we have to figure out what's wrong and what's new and where they come from. In 1964, Germain and others postulated that these particles are actually made of fundamental elements. It's called the quarks. It's very similar to elementary tables, table of elements. So you have hundreds of them. But here, he only assumed there are three types of quarks. He called them up and down and strange. Originally, he thought that it's just up and down, but after that, he realized it's not enough, so he gave a strange name called the strange. And with these three quarks, he can make up all the existing, at that time, the so-called new particles. There are two types. One is meson, made of quark, antiquark, and there's another one that's made of three quarks. Like a proton, neutrons, we all know that. It's made of UUD or UDD, so it's three quarks. This is a very successful kind of theory, and indeed, after 5 years of this theory, he was awarded the Nobel Prize in 1969, because from his theory, we understood how to put all these discovered particles in a table in the same place, and we can even assume new particles, which was not discovered at that time, and afterwards, because of his prediction, we discovered. So this was a very successful kind of theory. But then there are two fundamental questions you can easily ask. Why only three types of quarks? Are there more? And why only two types of hadrons? Are there more? That's easy, right? I mean, his model is too simple that we always want to see if there are any kind of exceptions. Are there more complicated stuff existed in the nature? So indeed, if you put all this together, they have a UDS quarks. They have a charge minus 1/3 and the plus 2/3. And this is the new discovery. In 1974, Samtin and Bouton Richter discovered a new particles, which is called the Jepsi, and it is made of two new type of quarks, the C quark. See, this start to answer the question we just raised before. And later on, people find there are fifth quark. It's called the bottom or beauty. It's made of this upsilon and was discovered in 1977. And obviously, people think that you should have another one, it's top. And 1995, it was discovered. So the table kind of complete. But on the other hand, there's another series of new particles. The first one is electron, which was actually the first elementary particles, was discovered in 1897 by J.J. Thomson. But at that time, we did not realize all of this. But afterwards, when we discovered a heavier electron called the muon, which has exactly the same properties as electron, but just have higher kind of mass as kind of brother, and we start to think it's interesting. And associated with each lepton, we have a neutrino. So you have electron neutrino, and also you have a muon neutrino. So when you put all this together, you start to think, this is a very interesting picture. And indeed, everybody can predict there's even heavier lepton and another associated neutrino. So it looks like this table is almost complete and beautiful. Only 12 elementary particles. And you may ask another question. Are there more? No. So in LEP, the Large Electron Hadron Collider at CERN, we discovered that there are only 3 generations of neutrinos, corresponding to only 3 generations of all these elementary particles. So there are no more, only 12. Why? We don't know. So maybe you can later on discover why this is the case. But anyway, you see over this course, there are many, many Nobel Prize. They are major kind of discoveries. You put all these things together, as a summary, you see we have a so-called standard model of particle physics. You have 12 elementary particles, which made out of matter. Then we have 3 types of other particles, which intermediate interactions. Because particles, if you want to put them together, and if you want to have a change from one type to another, you have to go through so-called field and through interactions. And this field will mediate interactions and then make these particles all together. So you have photons, which are electromagnetic, responsible for photon. If particle has a charge, they go through this kind of electromagnetic interactions. And you have WZ, which are responsible for weak interactions. And after that, we realized they are actually the same type of particles or same kind of theory to describe these interactions. It's called the electroweak. And you have another type of particles called gluons. They are strong interactions. They bond all the quarks together to become a proton or become a neutron. So all of these interactions, these particles, they have been well understood, and the theory got the Nobel Prize for their formula, showing here in this cup. You see the formula is very simple, slightly more complicated than Newton's law, but more or less the same. And all the particles have been discovered, except one, which is so-called Higgs. Because the theory, you see here, if it had to be written in this form, particles like electrons, muons, taus, and the quarks, they should have no mass. They should have a 0 mass. In order to give them some mass, Higgs and other theorists in the 60s discovered or invented a new theory, and they claim that the whole universe are completely filled with a field called Higgs field. And this Higgs field have excitations, and this excitation give you a new particle called the Higgs. So if you see the Higgs particle, that means that there exists a Higgs field, and then all these particles, you see, which originally had no mass, because of their interactions with Higgs field, they got the mass afterwards. It's like a patch. Afterward, they got some mass. So logically, the system, the whole theory works. But the only problem is that whether Higgs, this particle, exists or not. And after more than 30 years of study, indeed, from 1964 to 2012, it's more than 50 years. And after many, many scientists, engineers, we worked together, and finally in 2012, this Higgs particle was discovered. So you can see that this is a beautiful picture, and everything has been discovered, and you may ask whether there's the end of particle physics. There are people talking this way. So indeed, there are more than 20 Nobel Prize over this course for this study of the structure and the theory of elementary particles. But we have 2 other fundamental questions. Whether this is the end of particle physics, or for young people, are there opportunities for your future as a particle physicist? So indeed, if you look a little bit more in detail, there are actually problems over the so-called standard model. One kind of problems are the experimental. First of all, the neutrino has a mass, which is not consistent with standard model. Secondly, there are a number of experimental evidence where the prediction and the measurement are not consistent. Another class of problems are theoretical. For example, if you look at the top mass and the Higgs mass, you find out that the vacuum is not in a stable region is in a so-called metastable region. It's not very, very stable. And also, if you look at this picture, we talked about this many times, there's the exact perfect symmetry between leptons and the quarks. Where it comes from, we don't know. And also, there's a question whether we are able to unify electroweak interactions and strong interactions. And also, we have to understand where the mass of Higgs come from, and mass difference of elementary particles, and also many other issues like dark matter and dark energy. I'm not going through all these details, but just tell you that there are actually a number of problems actually for experts that, or even for normal people, they can try to understand that there's something which is not very natural, there's something which need to be understood, and this is not the end of the field. So in summary, if you classify all the problems, they can be three types of problems. One is try to understand the ultimate constituent of matter. Study quarks, neutrinos, and try to understand if there are deeper structure of these so-called elementary particles. Secondly is to study interactions. We should study if Higgs itself is elementary particles, not maybe it's kind of composite kind of particles, and try to do, say, ground unification. And third class is try to understand its relationship with the evolution of the universe, in particular, dark matter particles and antimatter in our universe. It's a fundamental problem that we have right now. So if you look at the map of the experiment in the world on particle physics, they go to three directions: higher energy, higher precision, and also go to the cosmology. So we have an experiment trying to look for dark matter to understand why in the universe we have only matter, not the antimatter world. And we have many neutrino experiments trying to understand the properties of neutrinos. We have a dark matter search experiment, and also in space and underground. And also we have many of flavor physics experiments trying to understand the properties of this precision measurement of the standard model parameters. And we go to high energy. We have Large Hadron Collider at CERN, try to understand the new interactions, try to understand whether there are ground unification, and current experiment and also new experiments. So I'm not going through all the details a bit too much. I just pick up a few of them to give you an example what we're trying to do. So first of all is the Beijing Electron-Positron Collider. This is actually the beginning of the particle physics in China, and was started the construction in 84 to 88. And then afterwards, there was a major upgrade in the year of 2004, 2009. And that was actually my first experiment in China to build this detector. And the detector called the BESS-3 is actually a large international collaboration with more than 600 members from 84 institutions in 17 countries. There are a number of very important discoveries from this. The most famous one is this new particle called ZC3900. It is made of 4 quarks. Remember the question I just raised before, why there are only 2 types of matter made of 2 quarks as a methane, 3 quarks as a barrel. Now, this is the first time we found a particle made of 4 quarks. So this is a very interesting discovery, and it has been led us to a detailed study of similar kind of particles, and afterward there are many new similar particles were discovered. Along this line, we know that E plus minus collider is actually a very interesting kind of facility, and running at a lower energy for tau and the charm is not the ultimate future of particle physics in China. So we were talking about what could be done in the future. In 2012, once Higgs was discovered, we realized that a Higgs factory, E plus minus collider running at the energy right at the Higgs peak is actually the best choice for the future of particle physics in China. And this proposal actually gained the momentum in the world, and quickly many people start to follow this direction. And also in China, the project has been moved forward since then. So up to now, we have been working on this for almost 13 years. Indeed, over the course of these 13 years, the whole international community reached the consensus that a Higgs factory is actually the highest priority for the particle physics in the future. There were a number of countries had the study and reached the same conclusion, and also a number of proposals like CPC in China, FCC in CERN, IS in Japan, CLIC in CERN, that try to do almost the same thing. So you put all these 4 different Higgs factories at the same place, and you try to compare them, you can easily realize, first of all, circular collider has a higher luminosity. You see here, these 2 are circular and these 2 are linear. You see, circular has higher luminosity. And secondly, for circular collider, the tunnel can be reused for the proton machine. So indeed, economically, this is a good thing that you have a longer future. But on the other hand, the linear collider, even though at this energy point is not very, very advantageous, but it's very, very important in the future, because after the Higgs factory, if you really want to go to high energy, this is actually the only way you could go. So this is extremely technology that you had to preserve, and also hopefully there are new machines starting even from now to go along this direction. Of course, in addition to these 4, there are other discussions, in particular plasma weak field acceleration, which could be combined with kind of linear colliders as the future of particle physics. So indeed, in China, we started this CPC study. In 2013, we had the kickoff. 2015, we have a preliminary conceptual design report, and 2018, conceptual design report, and 2023, a technical design report. So the accelerator was designed in such a way that circumference is 100 kilometers. I forgot to mention, 100 kilometers is roughly the best kind of circumference. And the tunnel is going to house both E plus minus colliders and also the proton colliders. So even though we are not going to install a proton collider, but we can have a space reserved. So once you build the tunnel, you are thinking about future. And this kind of tunnel can give you a far future, up to 50 or even 70 years for particle physics. And this is the baseline parameters. In particular, if you pay attention to this plot, you can see that CPC can generate a quite high flux and a very high energy of gamma rays, which are actually better than or higher than most of the gamma ray sources, except this one, which has a slightly higher energy. So this is actually a multi-purpose machine, not only for E plus minus collider of Higgs generation, but also as a very powerful gamma ray source. So the study was on paper, of course, but also on the real apparatus. So over the last 13 years, we studied many of the prototypes of the equipment, and we covered mostly all the needed technologies. So we are kind of sure that this machine can be built. These are the list of studies we're going to proceed in the next few years and try to be fully ready for the construction. I'm not going through all the details. Just give you a planning schedule. You can see that in the next 5 years, the 15th five-year plan, start from 26 to 2030, we hoped we could get approval and start the civil construction, and later on in the next 5 years plan to finish all the construction, and the experiment can start in the year of 2036. hopefully. Now let me move to neutrinos. Neutrinos, you see, it's very important. We repeatedly tell you that matters are made of these two matrix, leptons and the quarks. In leptons, half of them are neutrinos. So total of 12 particles in which a quarter are the neutrinos. But neutrinos are very special. Now we know they have a little bit mass. The standard model actually set the mass to be 0, but cosmology requires that neutrinos have a tiny mass. And now we know that cosmology is right, particle physics is not right. So then we have to figure out exactly how to describe them and why and how exactly this can be described in a standard model. Up to now, we don't know yet. But there's a good news is that neutrino, if neutrino has a mass, they can actually oscillate from one type to another during the flight. It's called the neutrino oscillation. And this was proposed by a famous physicist, Italian physicist called Pontecorvo, and he really believes in communist ideology. So in 1950, he fled to Soviet Union, former Soviet Union, and stayed there until end of his life. And during that time in Soviet Union, he proposed this neutrino oscillation idea. Unfortunately, he died before it was experimentally discovered. Otherwise, he should get a Nobel Prize. So anyway, this kind of flavor oscillation can be described by this formula. It has two parameters. One is called amplitude, described as sine squared 2 theta, and also frequency, delta m squared. So frequency tells you how fast from one type oscillate to another. Amplitude tells you how big the changes is. Is 100% change to another type or only 10% change to another type? So these are the two very important parameters we are going to measure for the study of neutrino oscillation. Indeed, if you look at the formula, you see that there's a delta m squared, even though this is not absolute mass, but this gives you the most sensitive way to probe the neutrino mass. Indeed, now we can probe to neutrino mass to square of 10 to minus 5. If you take the square root, you can see that we are talking about 10 to minus 2 to 10 to minus 3 EV, which is a factor of 10 or factor of 100 smaller than current experimental limit. So you see that this is really a very sensitive kind of method. Neutrinos are everywhere around us. So from sky to down to the earth, everywhere. And the supernova, galaxy, Big Bang, the sun, reactor, accelerator, earth, and in particular our body. Every one of you actually emitting neutrinos every day at the level of 340 million. Okay, so it's a large number. You don't see it because neutrinos just can go through your body freely and harmlessly, so you don't feel it. So the neutrino oscillation with two flavors is a very simple formula. Once you have three flavor of neutrinos, the formula becomes slightly complicated, but you don't have to remember this formula. It's a 3 by 3 matrix, and you can decompose it, these 3 by 3, and become a 3 by 3 matrix. And this 3, you see, one is associated with so-called atmospheric neutrino oscillation. Another one is associated with solar neutrino oscillation. And the third one associated with mostly direct neutrino oscillation. And there's another matrix for the phase. In the past 27, almost 30 years, we start to measure all these parameters. Starting actually from 1998, we firstly observed the atmospheric neutrino oscillation and measured these two parameters by the Super K experiment in Japan. So Professor Kajita is going to show up, I think, the day after tomorrow, and he's going to tell you his discoveries of the atmospheric neutrino oscillation, which is exactly this experiment. And there's another experiment called the solar neutrino oscillation experiment by Snow in Canada, and they measured these two parameters. And in 2012, our experiment in Guangdong, about 2.5 hours flight from here, we measured another parameter called the θ13. So if you look at the whole table, you can easily realize that there are another 2 parameters or 1.5 parameters which is still unknown. One is the CP phase sitting here, and another one is the sine of daytime square 3.2, because here we only measure the absolute value, and now we want to know also what is the sine of this mass difference, mass square difference. So these are the situation about the neutrino physics. So in diabe, we try to understand these θ13 parameters, and fortunately, we managed to measure this value because this value is actually quite large. It's 0.09, very close to 0.1, 10%. When we start the experiment, everybody said this value should be small. It's about 0.01 or even less. And there are people arguing that there's no need to do this experiment because anyway, it's almost zeroed. But indeed, you see, it is not. It's very large. So in the end, you should keep in mind, although we have a good series here, keep in mind, don't listen to series. Do your experiment as you like. So this is our detector. And there are 4 detector modules sitting in the same place. So indeed, we have this one. It's called the far side. We have 2 near side with 2 modules. They immersed in the pure water to shield the detector from background, from the sky and also from the rock. So this is a setup of the detector, and you are going to see that all the neutrino experiments are quite similar. The A and the needs of mountain, and the B, they need a water pool to put your detector in so that you can shield your detector from background nearby. So after the diabe experiment, we came up with the idea of the Juno. It is actually located here in equal distance from 2 reactor complexes. One is called the Yangjiang, another one is called Taishan. Equal distance of about 60 kilometers, 53. The reason we choose this distance is because at the distance the oscillation maximum of θ12 here and this bottom, the sensitivity to the mass hierarchy is the highest, is the best. So you can see that at the experiment time of Cameron, they didn't know the oscillation pattern, and by chance the detector was here, and they are perfect. They just get halfway through. So it's about the 50% probability to see what they can see. So it's not the worst here and not the best here. So it's a very interesting kind of a coincidence. And other experiments you see here were too close because we didn't know where would be the best distance because the daytime square was unknown. So they all put the wrong distance. Of course, they didn't see anything. And the diabe and other experiment, because we know the daytime square, so we measure only the theta. So that's why we put our detector at the optimum baseline or best kind of distance. So the reason we start this experiment in Juno side here is also based on our experience because we have been working on react neutrinos in diabe, and we have been using liquid scintillator in diabe. So this is actually a continuation of our technologies. And this detector placed in this distance is actually give you the best sensitivity for the mass hierarchy. And this measurement is going to be independent from CP phase. Other experiment, the Hyper-K and the Dune in Japan and the US respectively, they measure, of course, also the sine, but they simultaneously also measure the CP. It's good that they are sensitive to both, but it's bad that they are dependent to each other. So we have to decompose this, and Juno gives you a very good independent complementary measurement. The reason we put the detector at equal distance is because in this case, your source is factor 2 higher, so your detector can be factor 2 smaller. So this is actually a way to save funding for your experiment. And indeed, we are lucky that at this best location, there's a little mountain here. It's not a city, it's not some, say, lake or something. It's a mountain, exactly what we want. So indeed, we are very lucky to be able to build this experiment here. The concept of this kind of react neutrino spectrum sensitive to the mass hierarchy is that you can see this is the original energy spectrum of the neutrinos from the reactor, and at the theta 1,2 oscillation maximum, the spectrum comes down like this. And if you look in detail, there's red and the blue. Red is normal hierarchy, red is inverted hierarchy, and blue is a normal hierarchy. So you have to be very sensitive to little wiggles, which means that you have to have very high statistics and also very good energy resolution. The energy resolution has to be better than datum 2.1 over datum 3.2, because what you try to measure is the difference of these two, is 1 plus or 1 minus. So your sensitivity had to be the same as this kind of datum 2.1. And unfortunately, this is 3%. This is almost let's say, the limit we could achieve with the energy resolution. If it's another factor of 10 smaller, then forget about it. There's no way you can do it. It's a factor 10 larger, then we are going to be very, very lucky. But unfortunately, the detector, this number, nature gave us this number just at the, let's say, technological limit. And we really have to push our technologies to be able to measure this 3%, which is corresponding to the energy resolution of here, 3%. I'm going to tell you later on how we achieve this 3%, but this detector placed in this place actually can do many, many other measurements. You see, for reactors, we can determine the neutrino mass ordering, and also in addition, we can measure neutrino mixing parameters, and you can see this is the current average uncertainties of all these parameters. With Juno, only 100 days, we can improve by almost factor 2, and for 6 years, we can improve by almost factor 10. So you can see that it's a very powerful kind of detector. In addition, we can study solar neutrinos, supernova neutrinos, atmospheric neutrinos, geoneutrinos, and also proton decays. So indeed, this is a multi-purpose detector with a very rich kind of physics potentials, and we plan to run this detector for more than 30 years. It is a large international collaboration. We have up to now 72 institutions from 17 countries. Total number of collaborators are 700, and you can see here there's a quite large fraction of collaborators from Thailand. Thailand. We have 3 groups from Thailand who actually played a very important role for this experiment. Later on, I'm going to tell you a little bit about it. So the detector is underneath a small mountain. Here, you can see here. So we built this underground laboratory with 2 axes. One is slope tunnel with 1.3 kilometers, and the slope is about 40%, which is the maximum allowed from engineering point of view. And then we have another vertical shaft, 600 meters, which is roughly about 200 floors of a high-rising building. The reason we know this because we tried to buy elevator. You cannot buy it because there's no exist of any elevators more than, let's say, at the level of, say, 200 stories. It's only 100, typical. So 300 the elevator you can find, 600 you cannot. So this is the detector concept. Again, you see we have water pool. We put our detector inside the water, and this is the structure of the detector. Inside we have an acrylic sphere which contains about 20 kilotons of liquid scintillator. Outside we have a steel structure which holds readout electronics, photomultipliers, and supporting structures for the Earth's magnetic field shielding. And this Earth's magnetic field shielding is a contribution from Thailand. We have also the top tracker and the water as a cosmic ray veto detector, and also on top we have a calibration house. So this is a picture. This is when we finished the construction of the detector. The red dot is the phototube, and then the white one is reflector. So in this case, with the reflector, you can reduce total needed number of phototube and get sufficient light from water. And this is the construction process. You see acrylic building. We start from bottom up for the steel structure, and then acrylic is start from the top down, from up to down. So every layer we hold this, you can see these holding bars, hold this acrylic panel, and then we layer by layer we go down on top of this supporting platform. And this platform can move up and down and also can change the diameter according to where it is in the sphere. And these are pictures when we finish all of them. And you can see this is the platform. At the very beginning, it was 28 meters above, and at the very end, it's only a few meters. So when we finish everything, we have to make sure that this acrylic has no defect. So we send workers, go through the whole sphere of this 35 meters diameter of acrylic, which is actually the largest in the world. And you can see these workers are actually going through every inches of the sphere to make sure there's no defect. And if there's any, you just send it out, which can actually preserve the lifetime of the acrylic. And indeed, this building, I noticed that when you come in, you see this hall with a structure. I noticed that it's a 5-story building, a bit more than 3 meters per layer, and 35 meters or 40 meters steel structure is about 13 to 15-story building. So factor 3 roughly larger than this building. So you can imagine how big it is in underground cavern. And indeed, the diameter of this underground cavern is 50 meters. At this moment, it's probably the second largest in the world. The largest one is Hyper K, which is just completed the construction of the cavern. So inside this water pool, we have water, and this water is our so-called veto detector. And this veto detector is made of water, so we have to control the temperature of water. We also have to control the background, radioactive background of the water, and we have to control many other things. So details I'm not going through, but I just want to point you that the Earth's magnetic field compensation coil is made by Thailand institutions. This is the bottom. You see, when we finish, we can easily put so many people, something like 30, 40 people, and you don't notice that. This is just at the edge, at the rear bottom of the detector. And this is a top. We have a top veto. It's a contribution of France and Italy. You see, when they finish, they put this picture there. So the Earth's magnetic field compensation is used to reduce the Earth's magnetic field by at least a factor of 10, so that our photo tubes can have 100% efficiency. So you can see this efficiency is actually as a function of the field. If you put this coil to reduce the field by, say, a factor of 10, then you can push the field seen by the phototube to this region, and then your efficiency can be maintained at the level of, say, 100%. So it's just, you see the picture here? It's just a coil like this, one by one, a total of 32 coils with a special direction, and the direction is measured when we dig out the hole, we go in, we measure the direction of Earth magnetic field, and make sure that this compensation oil is right exactly, let's say, aligned with the field. So it has been installed, it is running at this moment, and perfect, let's say. There's no problem at all. And also, in particular, all the measurements are actually in good agreement with the expectation. So the Earth's magnetic field down there, inside this coil, is just perfect. Her Royal Highness Princess had several visits to China, and in particular, he visited the Juno site. So she came down to the underground laboratory, and she saw where we are, and she was very much encouraged. And in particular, with her support, our Thailand institutions can have funding to be part of this experiment. So this is extremely important support. So this is how, when everything is finished. Okay, this is a picture. This is the photomultipliers which collect the light emitted from the liquid scintillator inside. This is the acrylic sphere. It looks like it's not smooth. There's some structure, but indeed it's not. It's a smooth acrylic sphere with a reflection of the phototube. So these dots are the reflection of the phototube. The phototube are placed in, you see, it's a very densely populated. That's because we would like to have sufficient large number of coverage of the detector so that we can reach so-called 3%. 3% energy resolution depends on total number of photons you collected. So with a kind of a sphere surface, we put a distance between two phototubes at the level of 3 millimeters. So with 3 millimeter clearance, we are able to cover the whole sphere of this acrylic at the level of 78%. So the whole area has been covered at the level of 78%. If you increase this clearance, let's say from 3 millimeters to 6 millimeters, you lose at least 5% of total coverage easily. So you can calculate. So once we finish the assembly construction of detector, we plan to fill the detector with the liquid scintillator. But before we fill it with liquid scintillator, we have to clean it because the radioactive background is a big problem for us. So once we finish, we invent a method to inject the moisture into the tank, into the sphere inside, like this. So we inject this moisture, the dust were attached to the moisture, and then they settle down and then they drop down to the floor. So by having this kind of operation for 2 days, we actually reduce the dust density by almost 2 orders of magnitude from so-called class 10,000 to class 100. So this is 2 orders of magnitude reduction of the dust inside the acrylic tank. So by doing this, we can have a very clean detector. And then afterwards, we had to remove the protective film at the inner surface of acrylic because otherwise exposed to air would permanently pollute the surface of the acrylic. So I'll show you this. So we wash the inner surface of the acrylic by almost 15 days, 2 weeks. Continuous flashing. First of all, remove the paper. It took us about 5 days. And then to remove all the dust attached to it. So it took us more than 2 weeks to finish everything. And in the end, now we measured that the surface is very, very clean. There's no dust. So once we finish all of this, we start to fill the detector with water. So inside and outside the acrylic, we fill both clean waters at the level of total amount of 60 kiloton or 65 kiloton with kind of required water quality requirement. In particular, radium thorium level is required to be 10 to minus 15 gram per gram. This is a very, very high kind of requirement. And then we had to make sure that during this feeding, the sphere is safe. The sphere is only 12 centimeter thick of the acrylic and very fragile, over 35 meters diameter. So we have measures, and we first make sure that the level of water is the same. Secondly, we make sure that the pressure, air pressure in out is the same. And then we have stress sensors to check whether the calculation and the measurement is the same. You see, they are the same. So all of this using so-called university physics knowledge. So if you have a second year of university kind of physics level, you can do all of the studies and you can be a major player of this experiment. So when we finish this cleaning with water, we have to generate a liquid scintillator. And this liquid scintillator are generated through several steps. First of all, a storage tank. Then we have aluminum oxide purification plant to remove dust. And then we have distillation to remove ions. And then we have mixing with PPO and the BSMB, which can generate light, goes through 1.8 kilometers of stainless steel pipe to underground with water washing and also gas stripping. And finally, we put the liquid into our detector. And we can only do it at the level of 7 tons per hour, so the whole process takes about 6 months, or even slightly more than 6 months. This is where we are. So up to now, we filled with about 20 cubic meters of liquid, and we have left over with another 4,000 cubic meters of liquid, which takes us about 1 month. And these are the measurement of the performance of this liquid scintillator. You see, we are actually in a very good shape. The light yield already measured to be more than 1,600 photoelectron per MeV. Our design was exactly this number. Sorry. Uh-oh. What happened? Can I get help? Sorry, I made a mistake. Go down, go down. Go down. Yes, 44. Okay, and in particular, you should pay attention to the background of uranium thorium, 10 to minus 17 gram per gram, which corresponding to 8 milligrams of dust in 20 kiloton. So you see, this is a very, very small number. 8 milligram, if you go to floor, you touch it with your hand, it's more than, it's probably 1 gram of the dust, easily. So this is a very difficult kind of cleanliness requirement, but finally, I think we succeeded. And you can see the background. In particular, you notice that because there's no dust on the surface of acrylic, our single rate is very, very small. It's only 60 hertz, which exactly match our design. Most of the neutrino experiment existed. They all have problems with the surface dust because it's very hard to clean it. This high pressure water washing is actually very effective. So show you video, which probably give you a better feeling how we managed to reach the current status. So this is the civil construction, and there's no music. There was a music, but anyway, it doesn't matter. So you see the water during the digging, all the troubles we had, which made the construction almost 3 years of delay. And these kind of steel bars were so on the walls they drill holes and they inject these 20-30 meters long steel bars into the rock to fix the rock so that you get a stable kind of structure of the underground cavern. So the civil construction was not easy and complicated, and you see this is more or less the shape of the water pool. And then we start to build the detector. This is the stainless steel structure, 41 meters diameter, stainless steel. They were built from bottom up using screws. There are no welding at all underground. It's not allowed. It's all made of screws. So we have to make sure that 120 style and the screws, they can go into each other. You see, if you did not have sufficient good precision, they are not going to get through. You find you cannot put them all together. And this is acrylic. So acrylic, they made these panels of 12 centimeter thick, 8 meter long, and then they thermoforming into a spherical shape. With a spherical shape, then you make a big, let's say, sphere. You make it one by one, and then you inject the liquid to make it polymerization, and very much like glue, you put them all together. This is how it look like from top to bottom. You layer by layer going down. This is at the very end. And this is the last piece, a chimney. This is a moving of the platform, which I mentioned before. People working on this platform. And this is the photo tube. Installation of the tube, and this is when everything is more or less finished. This is how it looks like from inside when we finish everything. And these are the underwater electronics box. They are tested in the world deepest swimming pool in Italy, minus 40 meters. You see the number, 40 meters. That's the depth of the swimming pool. They are very proud. This is the world deepest water pool, minus 40 meters. This is a purification equipment for liquid scintillator. They have to transport it to the underground and then lift it up and then install it. And the liquid scintillator are mostly made of linear alkylate benzene. They have been transported from a city called Nanjing, not very far from Shanghai, over 2,000 kilometers. So a total of 1,000 container tanks have to ship from Nanjing to this place, and then filled into the detector. Okay, so that's all. We started from diabetes to Juno, and also we started from batch 3 to CPC. I think we have been seeing significant growth of particle physics in China, and we believe there's a great future, and we very welcome young people to join us. Thank you.
Question? Question, please. Yeah.
Hello, I'm Thanashort from Team Thailand, and I have some question like, what are the biggest challenge in reducing uncertainties on neutrino interaction cross sections, and how critical is that for oscillation studies? And other one for related, if Juno were to observe anomalies, how to afford it if it's more than the performance that prediction performance that you have?
The biggest challenge for this experiment actually is to achieve the energy resolution, which mostly depend on how many of the photons you can collect. So very much depend on the coverage I just explained, depend on the detector quantum efficiency to photons, and also depend on the transparency of the liquid scintillator. So photons generated inside the big detector has to be able to come out. So liquid has to be transparent that you can get the photon out. So these are the key parameters, and I have been shown a little bit here. And if this can be achieved, our physics goal of the mass hierarchy measurement can be achieved, and I think that's a goal. So.
Okay, thank you.
Wang 院士您好. I am Hao Chen Song from China, and I have a question regarding the circular electron collider, CEPC. It's certain that CEPC is essential for the next breakthrough of the high energy physics field, likely about the study of the nature of Higgs, particle Higgs. And there have a lot of, but there have been a lot of criticisms, mainly from outsiders, saying that collider hardly yield practical benefits compared to other fields of research. They said so by assuming that the achievements brought by the CEPC in high energy field could only have a real effects long after. So I want to ask about your opinions toward that. Yeah, thanks.
Yes, everybody try to have their opinions about how particle physics should move forward. Indeed, we never criticize biologists or condensed matter scientists why they should do their research. I think every discipline have their own logic, how the field should move forward, what is best way to do their research. And every discipline have to do things right to advance the study. Now, particle physics, of course, have their own logic. I just showed you before that Higgs is the highest priority from our own internal logic. And usefulness for society, of course, there are some, let's say, side effects, some outreach effects, and so on. Of course, there are. But it's hard to predict. And people, why they criticize particle physics, because we have only one project, and and we construct this for 10 years. So it's very visible. For other quote-unquote small scientists, they spend also a lot of money in their lab. If you multiply number of labs, multiply number of years, particle physics are actually spending less than those quote-unquote smaller type of scientific research. So when you talk about why we are expensive, if you divide by number of people, divide by number of years, we are not more expensive. We're cheaper than others. And we are more efficient because we are sharing the facility. And we collectively study the best approach, best way to do our study. I think we have better efficiency than other fields.
Yeah, thank you, sir.
Yeah, over there, please, yeah. Okay. There, please. Question, yeah.
Oh, thank you for your exciting lectures. I heard about the quartz and lepton. There are 12 core terms, and I think it is too so many core terms to explain about the nature systems. So I think the more fundamental system than the particle physics. And I want to ask Ed, how do you think about it?
I'm not sure I understand your question. There are 12 elemental particles, not photons, six leptons and 6 quarks. They are fundamental at this moment.
So the number of 12 is so large, I think, to explain the nature system. So I think the more fundamental system than the particle physics and more clearly and easy to explain the nature.
Up to this moment, particle physics is the most fundamental understanding of the ultimate structure of matter.
Yeah, I know, but I want to hear about how do you think about it?
I think that's right. What I'm saying is what I believe.
Okay, thank you.
Hello, I'm Sirawut from Thailand. I have a question related to gravity. So gravity is one of the fundamental forces in the universe. However, some scientists don't usually observe it because it is not detectable when the masses of objects are small. So my question is it true that gravity is not present if the object has a very small mass, and does it have any effect on some fundamental particles such as neutrinos?
Well, I mean, you learn the gravity from schools. They are not zero. They can be small. It's just relative. So even for neutrinos with very little mass, of course, they have gravity. And the fact that it's small doesn't mean that it doesn't exist. The problem for us now is to unify the, let's say, electroweak and the strong interactions with gravity. And this has difficulties because fundamentally they are so different that, and to be unified, you need a lot more effort. It is not completely impossible. Mathematically, there are a lot of suggestions. Theoretically, I mean, there are theories, but it just becomes so small that it's hard to test whether it's right or not.
Thank you.
Good afternoon. My name is Ponggon from Thailand. Thank you for your fascinating lecture. My question is about what is your upcoming objective after reaching the conclusion of the hierarchy problems, and what can us young people contribute to this project after this?
Of course, I have no solutions, otherwise I will tell you. So we need you to solve the problem.
Thank you.
Hello, sir. I'm Simil from Myanmar. I have two short questions. For the first one, since neutrino oscillation implies non-zero max, does that mean the standard model must be extended? And the second one, what are the main experimental challenges in measuring tiny neutrino max differences?
I'm not sure I understood your first question. What
Uh,
was your first question?
Neutrino oscillation implies to non-zero max. Does this mean the standard model must be extended?
Yes, with the neutrino oscillation, we prove that neutrino has to have a mass. So standard model, which originally set neutrino mass to be 0, is not correct. It has to be modified, but the exact way to modify it, we don't know. It very much depends on property of neutrinos, which we still have to understand. So there's a big hole there. Of course, very much depend on young people's contributions in this room. Your second question was neutrino mass so tiny, right? You see the number, and measuring the neutrinos is very hard. The best way up to now is through beta decays. And through beta decays, we only reach a level of 0.4 EV, which is already a very small number. You know, the weight of an electron is 500 keV. So factor of 1 million higher than the neutrino mass, at least. So that's why it's hard.
Okay, sir. Thank you so much.
Good afternoon. My name is Shayudwana Sintop. My question here is about the experiment, Juno experiment. So my question here is that how many times was the system has been tested, or have it been failed before?
This is a very large experiment. There's no way you can build one prototype to test it. So we only test piece by piece in small scale. For example, we have 20,000 phototubes. We test 1, we test 2, test 10. And then we produce them all, 20,000, and then we mount them. Of course, there are a few which are bad. We just take them out. And for the steel structure, there's only 1. So we have calculation. We do measure the stress. That's why I show you, we try to measure step by step the stress to make sure that there's no, let's say, surprises. In the end, steel structure is okay. For acrylic, we do have problems. We have some cracks, some imperfections. That's why we repair them. And after repair, we mount people there to inspect by eye to see if there's any further problems. So we try our best to do all the possible tests, but not everyone with, let's say, perfect one-to-one test. So we still have to rely on extrapolation.
Okay, thank you, sir.
Thank you.
Hello, my name is Indy and I'm from Thailand. Well, since Juno experiment is designed to determine the precision of the neutrinos, I want to know the impact of the results of the experiment to a higher understanding about neutrinos and how it could possibly relate it to like a deeper symmetry, like a seesaw symmetry.
Good question.
Thank you.
First of all, the Juno experiment has its own very definite kind of physics goals, which can answer a few questions, as I said, the mass hierarchy. And this mass hierarchy, together with other experiments in the world, we can collectively measure the CP phase and the mass hierarchy. After both of these two parameters are measured, we probably can try to understand leptongenesis, understand why the matter and the antimatter is not symmetric, and understand the problem afterwards. So Juno itself is not going to answer all the questions, as you mentioned, ultimate questions, but together with others, and probably with the other future experiment which is not yet designed for, maybe we can understand some of these problems. So still, not very near future, we can understand the problem you just posed for. It takes time.
All right, thank you.
So My name is Tan Chanon from Thailand. So my question is about CEPC. According to CEPC, have the potential to reach the new era for the precision measurement and for the continuous-based discovery. So my question is, how do you foresee its role to inspiring and integrating the young scientists, particularly from the developing country?
CPC is a very large facility, and it employs extremely demanding advanced technologies. So people join this effort, you can learn many things technology-wise. And of course, on top of it, we have a great list of physical potential. So from science point of view, you can also answer many, many questions. Of course, it's a very complex facility. No country can do it by its own. So it is going to be a large international facility, and the countries like developing countries in particular can come to join and work together. So partially contribute to the facility and partially solve one of the or few of the list of the scientific problems. And that collectively work with others is actually a good way for developing countries to be quickly catch up to the level of the developed countries because you are working together. So you can catch up quickly. It's quicker than just do it by yourself in your own country, in your own small lab.
Thank you.
I'm sorry, I have to stop because I think we bring the question to the camp, okay? Yeah, we have camp about 1 hour, okay? Now it's really too long already, okay? Yeah. We thank the speaker, please. Yeah.